Good morning. Today we are going to start the chapter Ethers and Epoxides. Introduction. Organic compounds having carbon, oxygen, carbon as the functional group are called ethers. Their general formula is ROR dash, where R and R may be same or different alkyl or aryl groups, or one of them may be an alkyl group and the other aryl group. The divalent oxygen is also called the ethereal oxygen. Ethers in which the group R and R dash are the same are called simple or symmetrical ethers, while those in which the group R and R dash are different are called mixed or unsymmetrical ethers. Ethers may be regarded as the functional isomers of alcohols. For example, both dimethyl ether and ethyl alcohols have the same molecular formula, C2H6O, but different functional groups. Classification. Ethers may be broadly classified into the following three categories. First, aliphatic ethers, in which R and R dash may be saturated or unsaturated groups derived from aliphatic hydrocarbons. For example, ethyl methyl ether, that is saturated, methyl vinyl ether, unsaturated. Aromatic ethers, in which either one or both groups are aryl groups. For example, methyl phenyl ether or ethyl phenyl ether. Aromatic ethers are further subdivided into phenolic ethers and diaryl ethers. Ethers in which one of the groups is aryl while the other is alkyl are called phenolic ethers or alkyl aryl ethers. On the other hand, ethers in which both the groups are aryl are called diaryl ethers. For example, methylphenyl ether, phenolic ether, and diphenyl ether is an example of diaryl ether. Third, cyclic ethers. Ethers in which the oxygen is present in a ring are called cyclic ethers. They are further classified as simple cyclic ethers or crown ethers. Simple cyclic ethers. Cyclic ethers containing 1, 2, or 3 oxygen atoms in the ring are called simple cyclic ethers. For example, oxirane, oxetane, tetrahydrofuran THF. Crown ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because their three-dimensional shape resembles the shape of a crown. They are usually named as X crown Y, where X is the number of atoms in the ring and Y is the number of oxygen atoms. For example, 12 crown 4, 15 crown 5, 18 crown 6. Nomenclature. First, open chain or acyclic ether. Common names. The common names of ether are derived by naming the two alkyl or aryl groups linked to the oxygen atom in alphabetical orders and adding the word ether. In case of symmetrical ethers, the prefix di is used before the name of alkyl or aryl group. Some aromatic ethers, however, have their special names. For example, methyl phenyl ether is called anisole and ethyl phenyl ether is called pentanol. IUPAC names. In the IUPAC system, ethers are named as alkoxyalkanes. The ethereal oxygen is taken with the smaller alkyl group and forms a part of alkoxy group, while the larger alkyl group is considered to be the part of alkane. Acyclic polyethers. Long chain polyethers are named as oxa, derivative of alkane, corresponding to the total number of carbon and oxygen atoms present in the chain. Cyclic ethers. Common names. In the common system, the three-membered cyclic ethers are named as oxides of the alkylene from which they are derived. The names of some cyclic ethers are based upon the names of their fully hydrogenated products. IUPAC names. The IUPAC names of cyclic ethers CH2O whole N, where N 2, 3, 4, 5, 6 are given below. For example, if n is equals to 2, it is called oxirane. If it is n is equals to 3, oxetane. 4, it is oxolane. And for 5, it is oxane. And for 6, it is oxipane. The italicized portion of these names are the suffix used to represent the size of saturated heterocycle rings other than with nitrogen atom. In case of substituted cyclic ethers, the substituents are indicated by numerical prefix with the oxygen atom getting number 1. Oxa names. Cyclic ethers are also named as oxa derivative of their corresponding cycloalkenes. Method of formation. Ethers can be prepared by the following general methods. First, from alkyl halides. Williamson synthesis. This is one of the best methods for the preparation of ethers. It involves the treatment of alkyl halide with the suitable sodium alkoxide. The sodium alkoxide needed for the purpose is prepared by the action of sodium on a suitable alcohol. The reaction in fact involves the nucleophilic displacement, or we can say substitution, of the halide ion from the alkyl halide by alkoxide ion by SN2 mechanism. Like halide ion, sulfate ion is a good leaving group. Therefore, in Williamson synthesis, alkyl halides may be replaced by alkyl sulfates. Limitations. A proper choice of alkyl halide and sodium alkoxide to be used in Williamson synthesis is necessary in view of following considerations. First, since a halogen attached to the double bond or an aromatic ring cannot be radially displaced by a nucleophilic reagent, therefore aryl halides are not generally used in Williamson synthesis. Therefore, for the synthesis of simple alkyl aryl ethers, the reaction is carried out between an alkyl halide and sodium phenoxide, and not between aryl halide and sodium alkoxide. However, if the halogen is activated by the presence of electron withdrawing group at ortho and para position with respect to the halogen atom, such activated aryl halides can be used in Williamson synthesis. Second, we have stated above the Williamson synthesis involves nucleophilic attack of the alkoxide phenoxide ion on an alkyl halide. Now, depending upon the structure, alkyl halide may undergo substitution or elimination reaction. Therefore, for the success of this reaction, it is essential that the alkyl halides used must be such with predominantly undergo nucleophilic substitution. Since primary alkyl halides are more susceptible to SN2 reaction, therefore best yields of unsymmetrical ethers are obtained when the alkyl halides are primary and alkoxide may be primary, secondary, or tertiary. For example, tert-butyl ethyl ether is prepared by treating ethyl bromide with sodium tert-butoxide. The above ether cannot be prepared by treating sodium ethoxide with tert-butyl chloride or bromide, since under these conditions an alkene, that is isobutylene, is the main product. With secondary alkyl halides, both substitution and elimination occur together, giving a mixture of ether and alkenes. But with tertiary alkyl halide, only elimination occurs, giving alkenes. Thus, when a mixture of tert-butyl bromide is treated with sodium ethoxide, tert-butyl ethyl ether is not formed, but instead 2-methylpropene is formed due to elimination reaction. Due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution. Reaction of alkyl halides with trisilver oxide. Ethers can also be prepared by heating an alkyl halide with trisilver oxide. From alcohols, ether may be prepared from alcohols as follows. By dehydration of alcohols. Ether may be prepared by dehydration of alcohol either in the presence of acid or heated alumina. First, acid catalyzed dehydration. Symmetrical ethers can be prepared by dehydration of alcohol with concentrated sulfuric acid at 413 Kelvin. Limitations. Though this method is useful for large-scale production of ethers, it has two major drawbacks. First, preparation of ethers is always accompanied by the formation of alkenes due to intramolecular dehydration of alcohols. However, in the case of 1 degree alcohols, the alkenes are formed only to a small extent, which can be further suppressed by using a large excess of alcohol. In case of secondary alcohols, alkenes are formed in much larger amounts than ether, but in case of 3 degree alcohols, exclusive formation of alkenes occurs. Thus, the order of dehydration of alcohol leading to the formation of ethers follows the sequence primary, then secondary, then tertiary. Therefore, dehydration of alcohol is used only for preparing ethers from primary alcohols. This method is not suitable for unsymmetrical ethers because a complex mixture of ether is always obtained. Mechanism. This reaction is an example of nucleophilic substitution reaction in which protonated alcohol molecule acts as a substrate, water as living group, and another molecule of alcohol as the nucleophile. The reaction may follow either first order kinetics or second order kinetics, depending upon the nature of alcohol used. In general, 1 degree alcohol follows second order kinetics mechanism, while 2 degree and 3 degree alcohols follows first order kinetics mechanism. Catalytic dehydration. Dehydration of alcohols to ethers can also be achieved by passing the vapors of alcohols over heated alumina at 523 Kelvin. By the action of diazomethane on alcohols or phenols, methyl ether can also be prepared in excellent yields by the action of diazomethane on alcohols or phenols in presence of tetrafluoroboric acid as catalyst. From alkenes, ethers can be prepared from reactive alkenes by the following two methods. First, direct addition of alcohols in presence of acid as catalyst. The main disadvantage of this method is that sometimes the initial formed carbocation rearranges to the more stable carbocation, which then reacts with alcohol to form rearranged ethers. Second, indirect addition of alcohol, alkoxymercuration reduction. Alkenes readily react with mercuric trifluoroacetate in the presence of an alcohol to give alkoxymercurial compounds, which upon reduction with NaBH4 in basic medium give ethers in high yields. The main advantage of this method over Williamson synthesis are: first, the reaction does not involve carbocation intermediates and hence there are no rearrangement in this reaction. And second, absence of competing elimination reaction. From Grignard reagent, higher ethers can be prepared by treating alpha haloethers with suitable Grignard reagents. Physical properties: physical state, color, and odor. Dimethyl ether and ethyl methyl ethers are gases at ordinary temperature, while the other lower homologues of ether are colorless liquid with characteristic ether smell. Dipolar nature. Because of the greater electronegativity of oxygen than carbon, carbon-oxygen bonds are slightly polar and thus have a dipole moment. Since the two carbon-oxygen bonds in ether are inclined to each other at the angle of 110 degrees, the two dipoles do not cancel each other. As a result, ethers have a dipole moment of 1.15 to 1.3 d. For example, the dipole moment of dimethyl ether is 1.3 d and that of diethyl ether is 1.18 d. Third, boiling points. Ether are isomeric with monohydric alcohols, but their boiling points are much lower than the isomeric alcohols. This is due to the reason that unlike alcohols, ether do not form hydrogen bonds. As a result, ethers do not show molecular association and hence have lower boiling points than the corresponding alcohols. Further, the weak polarity of carbon-oxygen bonds does not appreciably affect the boiling points of ether, which are about the same as those of alkenes with comparable molecular masses. Solubility. Ethers containing up to 3 carbon atoms are soluble in water. The solubility of other lower ethers in water is comparable to those of corresponding alcohols. For example, like ethanol, dimethyl ether is completely miscible with water. Similarly, both diethyl ether and N-butyl alcohols are soluble in water to the same extent. The solubility of lower ether in water is due to the formation of hydrogen bonds between water and ether molecules. As the molecular mass increases, the solubility of ethers in water decreases due to the corresponding increase in hydrocarbon portion of the molecule. Ethers are, however, fairly soluble in common organic solvents such as alcohol, benzene, chloroform, acetone, etc. Density: all ethers are lighter than water. Chemical properties: ether are relatively inert compound, almost as inert as alkanes. Under ordinary conditions, they are stable to bases, dilute acids, catalytic hydrogenation, and to most other reducing agents. This is due to the reason that the functional group of ether does not contain any active site in their molecule as compared to hydroxyl group of alcohols and phenols, even though the oxygen atom in both these functional groups contain two lone pairs of electrons. However, under specific conditions, ethers undergo the following reactions. First, reaction of the ethereal oxygen. On account of the presence of two lone pairs of electrons on the oxygen atom, ethers behave as a Lewis base and thus undergo reaction involving the formation of coordinate bonds as discussed below. Action of concentrated acid. Formation of oxonium salts. The oxygen atom in ethers have two lone pairs of electrons. As a result, ethers behave as Lewis base and thus dissolve in cold concentrated inorganic acid to form stable oxonium salts. Second, formation of coordination complexes. Being Lewis bases, ethers form coordination complexes known as etherates with Lewis acids such as BF3, AlCl3, FeCl3, Grignard reagent, etc. Due to formation of these complexes, Grignard reagent dissolve in either ether. That is why Grignard reagents are usually prepared in ether. They, however, cannot be prepared in benzene because benzene has no lone pairs of electron and hence cannot form complexes with them. Reactions involving the cleavage of carbon-oxygen bond with halogen acid. First, ethers are radially cleaved by hydroiodic acid or hydrobromic acid at 373 Kelvin to form an alcohol and an alkyl halide. However, if excess of acid is used, the alcohol first formed react further with the halogen acid to form corresponding alkyl halide. Similarly, cyclic ethers are radially cleaved by HBr or Hi to yield dihaloalkanes. Reactivity of halogen acids. The order of reactivity of halogen acids follows the sequence Hi, then HBr, then HCl. As discussed above, the cleavage of ethers by halogen acid in fact involves a nucleophilic attack of the halide ion on the protonated ether molecule. Obviously, greater the nucleophilicity of the halide ion, more reactive is the halogen acid. Since the nucleophilicity of the halide ion follows the sequence I negative Br and then Cl. Therefore, the reactivity of the halogen acids follows the same sequence Hi, Br and then HCl. Mechanism. The cleavage of ethers by halogen acids occur by the following mechanism. Step 1. Ethers being Lewis bases undergo protonation to form oxonium salts. Step 2. The protonated ethers thus formed undergo nucleophilic attack by the halide ion either by SN1 or by SN2 mechanism depending upon the nature of the group R and R' and the reaction conditions, to form a molecule of an alkyl halide with the displacement of weakly basic alcohol molecule. If the groups R and R' are primary, the reactions occur by SN2 mechanism, and if secondary or tertiary, the reactions occur by SN1 mechanism. Site of cleavage. The site of cleavage of unsymmetrical ethers by halogen acid depends upon the nature of groups R and R'. The following cases arises. First case, if both the groups R and R' are primary, The alkyl halide is always obtained from the smaller alkyl group. Second case, if one group is methyl or other is 1 degree or 2 degree alkyl group, the reaction occurs by SN2 mechanism. Due to steric hindrance, the halide ion always attack the smaller alkyl group, that is CH3 group, to give methyl iodide, while the bulkier alkyl groups gives the alcohol. Case third, if one group is methyl and the other is tert alkyl group, the reaction occurs by SN1 mechanism and the formation of product is controlled by the stability of carbocation resulting from the cleavage of carbon-oxygen bond in protonated ether. Since tert alkyl carbocation is much more stable than methyl carbocation, therefore the alkyl halide is always derived from tert alkyl group and alcohol from the smaller group, that is methyl group. It may be emphasized here that the higher polarity of solvent H2O present in concentrated HI has favored SN1 mechanism. However, if the cleavage of tert butyl methyl ether is carried out with anhydrous HI in ether, the low polarity of solvent would favor SN2 mechanism and hence I negative ion will attack the less hindered methyl group and methyl iodide will be formed and tert butyl alcohol will be formed. Case 4. Cleavage of alkyl aryl and diaryl ethers. In case of alkyl aryl ethers, the products are always phenol and an alkyl halide and never an aryl halide and an alcohol. The carbon atoms of the phenyl group are sp2 hybridized, while that of alkyl group are sp3 hybridized. Sp2 hybridized carbon being more electronegative repels a nucleophile, while sp3 hybridized carbon being less electronegative attracts the nucleophile. In other words, nucleophile attacks by the halide ion occurs more easily on alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, a phenyl group is much bigger in size than an alkyl group. Therefore, because of the steric hindrance of the bigger phenyl group, the halide ion attacks the alkyl group, leading to the formation of an alkyl halide and a phenol. It may, however, be noted that phenol is not converted to iodobenzene even with excess of HI. Diaryl ethers are not cleaved by HI because both the carbon atoms to which oxygen is attached are sp2 hybridized and hence repel the nucleophilic halide ions. Jessel method. Cleavage of alkyl aryl ethers by hydroiodic acid forms the basis of Jessel method for the estimation of alkoxy groups such as methoxy, ethoxy groups in such ethers. A known weight of the phenolic ether is treated with an excess of concentrated hydroiodic acid, the alkyl iodide produced as a result cleavage of ethers by HI is treated with an ethanolic solution of silver nitrate. The precipitate of silver iodide thus formed is filtered, washed, dried and weighed from the amount of HEI formed. The percentage of alkoxy groups can be estimated. With sulfuric acid, on heating with dilute sulfuric acid under pressure, ethers are hydrolyzed to alcohols. When heated with concentrated H2SO4, ethers react in the same manners as with halogen acids to form an alcohol and an alkyl hydrogen sulfate. Secondary and tertiary ethers, however, forms alkenes. Reactions involving the alkyl group. Action of air and light, auto-oxidation. Formation of peroxides. When close to air and light for a long time, ethers are oxidized to form hydroperoxide or simply peroxide. It is a free radical reaction and the oxidation occurs at the carbon atom next to the ethereal oxygen to form hydroperoxide. These peroxides are very dangerous compounds since they decompose violently at the high temperatures. Therefore, serious explosions may occur during distillation of old samples of ether if peroxides are not removed. Presence of peroxide in old samples of ethers may be detected by shaking them with a freshly prepared solution of FeSO4, followed by addition of KCNS. Appearance of a red color indicates the presence of peroxides. A simple method to remove peroxide is to shake an old sample of ether with either an aqueous solution or Ki or a ferrous sulfate when ether peroxides are reduced to ether. An I negative ion is oxidized to I2 or Fe2 positive salts are oxidized to Fe3 positive salts. Halogenation. Ether react with chlorine or bromine to give substitution products. The extent of halogenation, however, depends upon the reaction conditions. For example, diethyl ether react with chlorine in dark to give alpha alpha dash dichlorodiethyl ether. However, in presence of light and excess of chlorine, all the hydrogen atoms are substituted to give perchlorodiethyl ether. Now we will start epoxides. Three-membered cyclic ethers are called epoxides. In the common system, they are called alkyline oxides, but in the IUPAC system, they are called either alkyline oxide or epoxy alkanes or oxiranes. Synthesis of epoxide. There are two main laboratory methods for synthesis of epoxide. These are: first, epoxidation of alkenes. Alkenes on treatment with peroxy acids, also called peracids, such as perbenzoic acid, M-chloroperbenzoic acid, peroxytrifluoroacetic acid, etc. in an inert solvent such as CH2Cl2, CHCl3, or CCl4 gives epoxides. Due to the formation of epoxide, the oxidation of alkenes with peracids is commonly known as epoxidation. From halohydrines. When halohydrines prepared by addition of hypohalous acid to alkenes are treated with a base, HX is eliminated and an epoxide is formed. Here X is whether a chlorine or a bromine. Mechanism. It may be noted that synthesis of epoxide by base treatment of halohydrines is actually an intramolecular Williamson synthesis. Chemical reaction of epoxides. Acyclic ethers and cyclic ethers containing 5 and 6 member rings such as tetrahydrofuran and 1,4-dioxane are quite inert and are often used as solvents. 3-membered cyclic ethers, that is epoxides, on the other hand, are highly reactive. This is due to the reason that 3-member rings are highly strained, that is, they have considerable angle strain. Because of their highly strained nature, epoxide rings can be opened by a variety of nucleophilic reagents under much milder conditions. Consequently, most of the reactions of epoxides are the ring opening reactions, and these can be catalyzed by both acids and base. First, acid catalyzed ring cleavage of epoxide. Due to the large angle strain, epoxide are readily hydrolyzed by dilute mineral acid at room temperature to form corresponding 1,2-diols, or we can say glycols. Mechanism. In the acid catalyzed hydrolysis of epoxide, the oxygen atom of the epoxide ring first accepts a proton to form protonated epoxide. The protonated epoxide then undergoes nucleophilic attack, that is, second order kinetic mechanism is followed by water to give a trans 1,2-diol. Second, base catalyzed ring cleavage of epoxide. Unlike ordinary ethers, epoxide can also be cleaved under basic conditions. Mechanism. Due to greater electronegativity of oxygen than carbon, the carbon atom of the epoxide ring carries a small positive charge and hence can be easily attacked by strong nucleophiles such as hydroxide, alkoxide, phenoxide, ammonia, amines, etc. Regioselectivity or orientation of cleavage of epoxide. Unsymmetrical epoxide can undergo ring opening in two different directions and hence can give different products under acidic and basic conditions. In acidic medium, the nucleophile generally attacks the more substituted carbon, while in basic, the nucleophile attacks the less substituted carbon. Although both the reactions occurs by the same SN2 mechanism, the difference lies in the stability of their transition states. In the acid catalyzed cleavage of epoxides due to protonation, each epoxide carbon atom carries a small positive charge, the magnitude of which depends upon the substitution. Since more highly substituted carbons can accommodate positive charge better, therefore more highly substituted carbon has a fair amount of carbocation character and hence get attacked by the nucleophile. In contrast, in base catalyzed reaction, there is no protonation, hence none of the epoxide carbon has a fair amount of carbocation character. Therefore, like SN2 mechanism reactions, the attack of nucleophile is controlled by steric factor. Evidently, the nucleophilic attack will occur preferentially at the less hindered carbon atom. Stereochemistry of ring cleavage of epoxide. Both acid and base catalyzed ring opening reactions of epoxide occur by SN2 mechanism. Therefore, attack of nucleophile always occurs from the backside, leading to the formation of trans 1,2-diol. Reactions with Grignard reagent and organolithium reagents. Epoxides are also undergo ring opening reactions with Grignard reagents and organolithium compounds. The addition products initially formed upon hydrolysis gives primary alcohols containing two carbon atoms more than the Grignard or the organolithium compounds. The epoxide generally used in these reactions is ethylene oxide. Hence, this was it from the chapter. Thank you.